Hi everybody. This video is about my newest, most sophisticated, and most maneuverable actively controlled model rocket called Diamond X. But before we get into its design and first flight, let's take a trip through the last 2 years to see how I got here. The Diamond series of rockets originated just after I graduated college, and I thought it would be really cool to develop a hot launch silo to fire rockets out of. This silo is called Atlas. It uses 8 internal aluminum rails in pairs sandwiching each fin to guide the rocket. It has a silo door that opens on command and a flame trench system to redirect the rocket's hot exhaust gases. Unlike cold launch silos, which throw the rocket into the air before its engine ignites, hot launching requires igniting the engine inside of this box. This system also needed a new rocket which could interface with the silo's internal rail system and the networking infrastructure that supports it. Both of these would heavily leverage 3D printing for most of their construction. It was a technique that I was just getting used to at the time, but is pretty approachable. Over the next year, I worked on the silo itself, the rocket to fire from it, and the data link and ground control software to communicate with everything. I was going for a Mark 41 style launcher here, where the hot exhaust gases are redirected upwards through a flame trench, and then they come out right next to where the rocket is. I thought it looked super cool. In this first iteration, to bend this hot exhaust gases 180 degrees, I used a single piece of thin sheet steel bent into a U-shape. I static tested the silo with some fixed D-class Estes motors, and realized pretty quickly that the steel piece wasn't going to cut it. So I changed up the flame trench material to use high temperature ceramic plates, which are actually just regular flooring tile that I cut and kind of bent into a U-shape. Both the silo and the rocket communicate with the laptop ground control software with 900 MHz radios. I can receive telemetry from both and then send commands to each one. Diamond 1 was the first rocket designed for this new silo. It used fixed aft fins for stability and actuated canards for pitch, yaw, and roll control. And its ground control software let me do everything from calibrating its gyros to aligning its fins, getting everything ready for launch all at a distance. It used a custom flight computer and a 3D printed avionics housing, and had its own telemetry radio in the nose. The rocket software was tested extensively on the ground, and then I did fit checks to ensure that it slid into the silo nicely and that it would leave without hitting anything. So with everything ready, it was time for our very first test flight.
Doors, 3, 2, 1, launch!
So this test didn't go great. Tip for you rocketeers out there, starting with a relaxed stability design where the vehicle is statically very marginally stable, absolutely not the way to go. But I learned a lot, so it was time to make a new rocket and fire it again. So over the next couple of months, I built a Diamond 2, a very similar design, but with a few software and hardware changes. It had an increased stability margin, and also better data logging for more post-flight analysis. Diamond 2 flew from the silo for its first test and suffered similar controllability problems. I had some very aggressive control gains, and they were highlighting some issues with canard-control vehicles with fixed fin cans. But the silo system and all the onboard software worked great, safely recovering the vehicle, and I logged all of its flight data. I also got really great footage from the GoPros next to the pad. So after this launch, I dove into some CFD to figure out how I could improve the design, and I got a lot more familiar with the aerodynamic problems associated with canard control. To make a very long story short, the actuated fins shed vortices both from the leading edge and from the canard tips. These vortices then flow backwards and hit the static fins in the back. This can cause all sorts of funky aerodynamic problems. The big one is roll reversal, where the rocket spins the opposite direction you want it to if you deflect your fins too much, which is a function of airspeed and angle of attack and all sorts of stuff. It can also decrease the pitch and yaw controllability, or sometimes increase the pitch and yaw controllability. It'll also even decrease the whole rocket's stability margin if you deflect them too much. If they go too far, then they disrupt the airflow over the aft fins, which was definitely a contributing factor to some of these. I had these fins deflecting like 20 degrees, 30 degrees, which is way too much. So for the following flights, I toned that way down. Another thing that I did was I modified the canards with a much lower leading edge sweep angle, and it was flown from a rail several times. One concern that I had was that the exhaust gases from the flame trench were causing a local negative airspeed on launch. Although looking back, I don't think this was really an issue, and so we're going to pick up some more silo flights in the future. I called this configuration Diamond 2B with the straighter canards, and it flew twice. It gathered really good data on roll control and the limits of roll control with its canard design. In order to solve these control problems, I wanted to transition to aft fin control. With this system, the control surfaces, now located at the back of the rocket, would still produce vortices, but they wouldn't impinge in any part of the vehicle. They would just drift off into the free stream. This, in theory, would make the rocket way easier to model and simulate because I don't have to model those interference effects. Unfortunately, it would mean I need to cram the rocket motor, the fin servos, the fin mounting mechanism, and interfaces for all that into a very small space at the back of the rocket. So I started with a larger airframe to get some experience designing this type of aft motor mount / fin can assembly. This led to Shock, a 3-inch diameter rocket testbed for both aft fin control and a number of other things like onboard cameras and a very cool solid rocket motor attitude control system called ACES. I'm going to have more videos on this coming soon. Shock has flown 5 times so far, and its design helped me understand a whole lot. How to build this aft fin control assembly was one of them, how to make the cable harness and the raceway shroud that takes data from the flight computer at the nose to the servos in the back. This system has to separate in the middle, so this cable needs a connector there. It also helped me validate some MATLAB simulation tools that I'd developed, which I was having a really hard time squaring with the canard-control data due to those interference effects we talked about. I have a couple dedicated videos on Shock on my channel, which you can look at if you're interested. After these flights, I was confident that I could shrink the outer diameter of the fin and motor mount assembly to fit into a 2.56-inch airframe. And that leads us to Diamond X. Diamond X is about 0.8 meters long and 1 kilo in weight. It flies on Cesaroni 29mm rocket motors, and it can reach up to 1,200 meters in simulations. Translating for freedom units, which is just about 4,000 feet. The rocket has 3 main sections, not unlike most amateur rockets. From nose to tail, they are the avionics assembly, the recovery system, and the motor mount, and in this case also includes the control system. It uses standard cardboard airframe, which is very lightweight, and mostly 3D printed parts for everything else. There are 2 core systems at the heart of this rocket which make it my most compact and maneuverable yet. The first is this ultra-compact fin and motor mount assembly. This main piece is printed as a single part in carbon fiber reinforced polycarbonate, a very strong and rigid material. It weighs about 80 grams and mounts the fin servos, the fins, their bearings, the linkages, a motor insulation sleeve, and the rocket motor, all in that space. Each fin has its own BMS A10 servo and 2 bearings. These tubes here are the mounting system for a booster, which is going to be flown in some upcoming flights, very cool. The second key improvement is the stackable avionics assembly in the rocket's nose. This is a spiral on the Shock avionics system, so they're mostly the same, they're just reorganized in a different form factor. In this case, it's 2 custom PCBs, and they do everything that took 4 PCBs in Shock to accomplish. The biggest change is stacking a set of circular boards and mounting them normal to the rocket's long axis, instead of making a single large rectangular one and mounting it vertically. By stacking the boards this way, they take up way less longitudinal space on the rocket, meaning the avionics compartment can be much shorter and more compact. So again, I can do everything that Shock avionics stack does in a fraction of the mass and volume. This avionics system runs on a version of my common flight software, which is shared between all the different rockets that I fly. So if I make an improvement to one of them to make their control system more precise, it also affects the others to make them more accurate and more precise as well. Each rocket then has its own set of aerodynamic parameters and control gains, and these control gains were derived from simulations with the tools that had been developed with Shock flights. Before we flew, a whole bunch of ground testing was done to check the control system, the avionics data logging feature, and also the Kalman filter, which it uses to determine its position. With all that stuff set, it was ready for its very first launch in late September in 2023. So this rocket's guidance system on its first flight had a very simple mission: to point the rocket straight up, and then on the roll axis, it was told to hold the launch orientation with a plus 45 degree roll program at 3 seconds, returning to 0 at 5 seconds. Let's take a look at the video.
4, 3, 2, 1.
When you design a rocket for active control, there ends up being a lot of different design elements to balance. For example, the higher the rocket's stability margin, the less maneuverable it is. So you want a really high stability margin so that it comes off the rail cleanly, and if there's a control system problem, it's still stable. But if it's really stable, then you can't do the maneuvers you want to do, and you won't be able to do some fancier maneuvering techniques that you might have vision for down the road. Another one is that you can gear down your servos to make the fins very precise, but this will decrease their slew rate, which can lead to instabilities in control. You're also going to want really big controlled fins for maneuverability, but your servos are only so precise. So your control precision ends up a function of your servo precision, its linkage ratio, your airspeed, and the fin size and more. So there's a balance in how big your actuated fins need to be. In general, I found you need both actuated fins and static fins to get the stability that you want without sacrificing control precision. Finding a good balance in all of this is really difficult. It takes a lot of trial and error and experience, but my experience with earlier rockets was really helpful. Another big help was the simulation tools that had been verified in shock flights, where I could change these numbers, change fin sizes, slew rates, linkage ratios, and see what made the rocket perform the best. So this flight was a success. What's coming up next? There's a number of other really interesting control modes that I'd like to try. This control system just points the rocket vertically. It's controlling the rocket's Euler angles, yaw, pitch, and roll. But there are other techniques that you can use to control the rocket's position over the ground. So for example, if I want the rocket to stay immediately over the launch site, then it's going to need to actively kind of pitch around to adjust for the wind that it sees at altitude. So I'm going to try that soon. I also like to fly to some waypoints. That's an interesting one. So you could pick a waypoint calculated to be upwind so that your rocket flies there, deploys its parachute, and then it descends right to where you are. That way you don't have to hike a couple miles to go find it, like I did after this one. I've also been working on some first stage boosters that can be flown with all of my rockets in theory, but would start with Diamond X. The first of these uses a fixed high thrust 38mm motor. This is meant to fly from the Atlas silo, and the booster would get the vehicle up to speed and stable. I would then fly some longer burning, low thrust motors like H-53s or even H-13s on Diamond X itself. This combination would give me longer flight times at medium speeds and let me evaluate these other control modes better. In the distant future, I'd like to have a thrust vectoring booster to fly from the silo. I've been doing strictly fin control up to now, so this still has a lot of development ahead of it. That being said, a TVC booster with fin control upper stage flown from a hot launch silo would get me about as close to Mark 41 than I think any amateur has gotten so far. Now, don't get me wrong, this wouldn't be a very practical rocket to fly, very much a system of systems with very little redundancy, but undeniably it would look really, really cool. On top of all that, I'm working on a video about Shock's latest 3 test flights, which will be more engineering focused, getting into all of those nitty-gritty technical details. I also want to do more testing with ACES. I have built an entire system of hardware, software, simulation tools, and circuit boards for this attitude control system, and haven't flown it a single time. The reason is because it's probably not a very good idea. But I built the whole thing, I'm going to fly it at least once. So there's lots coming up to look forward to. Subscribe if you're interested and want to see more. I'll see you all in the next one.